Hello and welcome to this lecture. So we're going to look at a brief introduction to the circulant matrices and eigenvalues, eigenvectors, and particularly the important role played by roots of unity in the eigenvectors, eigenvalues of circulant matrices. Now circulant matrices are very common in electrical engineering. You'll see them soon enough, and maybe in the next lecture you'll see a more clear example of an application in electrical engineering where circulant matrices are used. Okay, so they're very central to all of electrical engineering, particularly signal processing. Okay, so let's start with an example. So in this first lecture, I'm going to give you a few examples to get you thinking about how this works. Okay, so here is a very simple example of a circulant matrix. So here is a nice, and it's got only ones and zeros. You know, how much more complicated can it be? So 1 0 1 1 1 0 0 1 1, and you can see the property here. Why is it called circulant? It's called circulant because you've got a first row, and then the second row is a cyclic right shift of the first row. So you can see that, no? What do I mean by cyclic right shift? Every element here is shifted once to the right. So this 1 came here, 0 came here, this 1 went all the way around, came here. Okay, so I hope you can see this. So it's a cyclic right shift. Similarly, the third row is a cyclic right shift of the second row. You can see that this 1 came here, this 1 came here, and this 0 turned around and went to the end. Okay, and if you do 0 1 1 cyclic shift, you will go back to the first row. So you can give circulating. Okay, so this is why it's called a circulant matrix. Okay. So now, how do I find out eigenvalues, eigenvectors? You can go ahead and find it. The first thing you should do always, this is our row sum idea. So if it's a circulant matrix, the same entries will come in every row. So the row sum will be the same. So 2 will be an eigenvalue and 1 1 1 will be an eigenvector with eigenvalue 2. So this is an easy thing for us to evaluate. And then you can find determinant A minus lambda I. You will see in this particular case it will work out like this. Because I know 2 is already a root, I can factor it out. So I'll get only a quadratic left. And for this quadratic, I can find out the roots. I'll find them. I'll get half minus I root 3 by 2 and then half plus I root 3 by 2. Okay. So now you can plug this in and find the eigenvectors. I'm not going to show you that calculation. It involves some complex matrices and all. You will get eigenvectors. 2 is easy. For this guy, you will get 1 minus half plus I root 3 by 2 minus half minus I root 3 by 2. For this guy also, you will get the conjugate. See, these two are conjugate eigenvalues, right? So now you know a real matrix with conjugate eigenvalues. Once you find one eigenvector, you don't have to find the next one. No, it's just conjugate. You just conjugate this, you'll get the answer. Okay, so keep that in mind. So these kind of tricks you should be able to use. Okay, so this is 3 eigenvectors. So you did that. Here's one more example, another matrix. So instead of 1 0 1, I've made it 1 2 1, and after that it's still circulant. So what happens here, notice something very interesting will happen. 4 again is an eigenvalue with there's an eigenvector corresponding to it. You can go through the same thing, you will get some equation like this, and then you can find eigenvalues like this, and you will get the same eigenvector. See, notice the eigenvalues would have been slightly different from the previous case. Okay, so 2 was different, and then you got this same guy. In this particular case, the same guy you got, but in general, maybe the eigenvalues will be different, but then the eigenvectors ended up being the same as before. Okay, so here are two different circulant matrices. Just because they were circulant, somehow magically the eigenvectors are ending up being the same. Okay, so something is going on here. What is going on? And to understand really what's going on, you need to look at this complex number, this half plus I root 3 by 2, half minus I root 3 by 2, whatever this complex number is, it's a special complex number. Okay, so we're going to see that number up close and why it is so special next. Okay, so that's the connection to complex cube roots of unity. Okay, so a little bit of a refresher of complex algebra and numbers for you. This number minus half plus I root 3 by 2, which showed up a lot in our examples, I'm going to call it W3. Okay, omega 3 if you want. Okay, so omega 3 or W3 or something like that. So I can represent it in the complex plane. So this is my complex plane. I have the real numbers in the x-axis, imaginary numbers, imaginary component, real component in the x-axis, imaginary component in the y-axis. Every point in this plane is a complex number, you know, x plus iy. Okay, this is a unit circle, and I've shown a 1 here because this point is 1. So it's a unit circle. Its radius is 1. Okay, so this omega 3 or W3 happens to have absolute value 1. You can see it. 1 by 4 plus 3 by 4 is 1. So it will lie on the unit circle. Where will it lie? It will lie with x coordinate real part minus half and y coordinate or complex part root 3 by 2. So that's where it lies. Okay. So now from your trigonometry and angles and all of that, you should know that this corresponds to an angle of 2 pi by 3. Okay. So what you have here as omega 3 is actually cos 2 pi by 3, which is minus half, plus I into sine 2 pi by 3, which is root 3 by 2, and together we see that this guy is nothing but e power I 2 pi by 3. So all this we have seen earlier. So this is a very, very important observation. So this omega 3, this minus half plus I root 3 by 2, which ended up showing up all the time in our circulant matrix eigenvalue, eigenvector computation, is actually a complex number. It's on the unit circle and it is e power I 2 pi by 3. The angle is 2 pi by 3 in the anticlockwise direction. Okay. So now the next important thing to look at for us is multiplication by this omega 3. Supposing you multiply by omega 3, multiply a complex number by this omega 3, what exactly happens? Okay. So here is this an arbitrary complex number z. Maybe the the polar representation is r e power I theta. Okay, r is the magnitude, theta is the angle, right? So this is the complex number z. Now when I multiply this by omega 3, what actually happens is omega 3 z ends up being r times e power I theta plus 2 pi by 3, right? So this is only e power I 2 pi by 3, the magnitude doesn't change, only the angle changes. In fact, the angle basically rotates to the left anti-clockwise by 2 pi by 3 and you get omega 3 times z. So multiplication by omega 3 is nothing but this kind of 2 pi by 3 rotation. So that's a good intuition to have. A lot of times the algebra can be a little bit confusing. So this multiplication being rotation anti-clockwise by 2 pi by 3 is very important. So armed with this idea of multiplication, we can now figure out powers of omega 3. So omega 3 powers are very important. So omega 3 squared, if you want to do, it's omega 3 times omega 3. So omega 3 is here. I'm going to multiply this guy with omega 3. So any multiplication is what? It's a rotation by 2 pi by 3. So you're already at 2 pi by 3. If you multiply by another omega 3, you're going to go to 4 pi by 3. And that's what happens here. So you just rotate by 2 pi by 3. So you can also do it algebraically, e power I 2 pi by 3 times e power I 2 pi by 3, you'll get e power I 4 pi by 3. So all these guys are the exact same thing. Now this e power I 4 pi by 3, if you actually evaluate its coordinates, it will end up being minus half minus root 3 by 2 I. Okay. And in fact, it's the complex conjugate of omega 3. Okay. So this omega 3 square ends up being the complex conjugate of omega 3. So here is a nice little representation for where omega 3 squared will come. What about omega 3 power 3? It is 2 pi, just multiplying once again. So you're already at 4 pi by 3. I have to multiply by another 2 pi by 3. So it's just rotating again by another 2 pi by 3. Where will I go? E power I 6 pi by 3. And 6 pi by 3 is nothing but 2 pi and that is nothing but 1. Okay. So omega 3 power 3 ends up being 1. Okay. So this is where we have cube roots of unity. So this omega 3 is a cube root of unity. It satisfies this nice property that if you raise it to the power 3, you get 1. Okay. So you can see 2 pi by 3 is here and then square and then this rotation, it goes down to 1. Okay, so now if you take higher powers, you will just get repetition, right? So omega 3 power 4 will just become omega 3, omega 3 power 5 will be omega 3 squared, omega 3 power 6 will again be 1 and so on. It's just rotation, 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 rotation. The three values, it will keep rotating over and over again. Okay, so what are my cube roots of unity? The three of them are 1, omega 3 and omega 3 squared. Okay, so why are they the cube roots of unity? If you cube them, you get 1. And they are the three solutions of x power 3 minus 1 equals 0. There are no other cube roots of unity, right? You may say omega 3 power 4, 5 and all, but eventually it comes back to one of these three numbers, right? There are no other numbers which will raise to the power 3, you will get 1. Okay, I hope you see this. So this is the complex cube roots of unity. I'm going to use this omega 3 notation a lot. And then there's one more idea that's important. Where does the circular cyclic shift and all come in? Okay, and what is the connection with the cube roots of unity? Okay, so there is this very subtle and interesting connection. Let's say beta is an arbitrary cube root of unity. Only three of them are there. So it could be 1 or omega 3 or omega 3 squared. Omega 3 is this guy. So I know this is my cube root of unity. I'm going to define a cube root vector which I call 1 beta beta squared. Okay. So for instance, if beta is 1, this vector is just 1 1 1. If beta is omega 3, it is 1 omega 3 squared. Okay. If beta is omega 3 squared, it is 1 omega 3 squared, omega 3 power 4, but omega 3 power 4 is same as omega 3. Okay. So this is the cube root vector. Why did I define a cube root vector? Because I'm going to define something with it which is useful in understanding an input vector and its cyclic right shift. So notice ABC, suppose ABC is your input vector. What is the cyclic right shift of ABC? CAB, right? AB goes to the right and then C comes back all the way around to the beginning. Okay, CAB. Okay. Now with these two vectors and the cube root vector, I can do something very interesting which I will call as a transform in quotes I won't go into detail here. It ends up being one type of transform which is very interesting in signal processing. So you take ABC and multiply on the right with this cube root vector 1 beta beta squared. What do you get? You get this scalar number A plus B beta plus C beta squared. Okay, simple enough. Okay. Now we can do the same for the right shifted vector CAB. Again you do the same transform, you get C plus A beta plus B beta squared. Why am I doing all this? Why am I doing this 1 beta beta squared and all that? So you see, this is the crucial point. Even though I got C plus A beta plus B beta squared, I can pull a beta common out. I get a A. Okay, if I pull a beta common out, I'll get a B beta. What will happen if I pull a beta common out from C? I will get C beta squared. Why? Because beta is a cube root of unity, beta power 3 is 1. Okay, so C beta squared times beta is actually 1. So it's the same as C. Okay, now herein comes the wonderful utility of this cube root vector and this transform. The operation of cyclic right shift in the transform domain, in the beta transform domain, is the same as multiplication by beta. If I cyclically right shift by 1, I might as well take the transform and multiply by beta and then go back to the vector. Okay, so that is the crucial crux here, the nice connection between cyclic shifts and multiplication by cube roots. Why did we get cube root? Because the vector was length 3. So I have to go to cube root. If the vector was length 4, I have to go to roots of x power 4, fourth roots of unity and all of that. Okay, so it will change based on the length of the vector. So in this particular case, it ended up being like this. Okay, so this property is very, very crucial. Supposing you do another shift, what will happen? You have to just take this guy and multiply by another beta, right? So if you see, you will get beta squared. So the first one shift is beta, the second shift is multiplication by beta squared. If you shift the third time, it's multiplication by beta power 3, but then beta power 3 is 1, so you go back to the same thing. So you keep going round and round and round like that. Okay, so that is the wonderful little connection between cyclic shifts of length 3 vectors and cube roots. Okay, so cyclic right shift by 1 is multiplication of transform by beta. Okay, so we're going to put this to use to attack an arbitrary circulant matrix. Here's an arbitrary circulant matrix ABC, CAB, BCA. Okay, I've done the same cyclic right shift and all that. I'm going to take a beta which is a cube root of unity. It could be 1 or omega 3 or omega 3 squared. We know this already. And here is my wonderful little idea. So I'm going to take this circulant matrix and multiply on the right with 1 beta beta squared. I'm going to try and do a transform of this entire matrix which is 1 beta beta squared. If I do that, I seemingly get this complicated looking polynomial thing, quadratic thing, right? So A plus B beta plus C beta squared, C plus A beta plus B beta squared, etc. Okay, but now I know already the first one was okay, the second guy was a cyclic right shift and I'm transforming again. So this should be just beta times the first fellow. The last guy should just be the beta squared times the first fellow. So if I pull out a plus B beta plus C beta squared, I simply get 1 beta beta squared. So notice how wonderfully this beta transform type thing has worked out. I've got an eigenvalue and an eigenvector for an arbitrary circulant matrix. Whatever my circulant matrix may be, this 1 beta beta squared, where beta is a cube root of unity, ends up being an eigenvector. So this is the crux of the idea here. So you get that the eigenvalues for different beta are just beta equals 1, you get A plus B plus C, beta equals omega 3, you get this guy, beta equals omega 3 squared, you get this guy. Here's just the substitution. You can, omega 3 power 4 is just omega 3, right? So you don't have to be scared of it. And here is the wonderful idea. The eigenvectors, you get 3 of them, 1, 1, 1, 1 omega 3 squared, 1 omega 3 squared, omega 3 power 4. In fact, you can show that these 3 are linearly independent and they make a basis for C3, not just R3, C3, right? So you get a basis for C3 here because these are all complex numbers and this works. The linear independence you can prove in multiple ways. I'm not going to prove it, but you can show that these 3 are linearly independent. Okay. So this is a very clean idea for 3 by 3 circulants and this can be extended to n by n circulant also. The later lecture will show you how to do that. Okay. So but this is sort of the important idea here. So what is very, very clean here is the eigenvectors do not depend on A and B and C. Okay. So that I always have found to be very fascinating. The eigenvectors for a circulant matrix do not depend on A, B, C. They are independent of it. Whatever may be A, B, C, the eigenvectors are the same. The eigenvalues though depend on A, B, C. They depend in some specific fashion like this. Okay, so this is a very fascinating result for circulant matrices. Okay, so you can do powers of a circulant matrix. I'm not going to go into detail here, except there is one little observation. For powers, I need S inverse, right? So this matrix looks ugly this S matrix as omega 3 squared and all, how am I going to do power? So S is easy and D is also easy, right? So you can define this lambda of x polynomial a plus bx plus cx squared and simply evaluate lambda at 1, lambda at omega 3, lambda at omega 3 squared, you get the eigenvalues. What about S inverse? You may think S inverse will be some very complicated thing, but using the properties of the cube roots of unity you can show. In particular, the property that's very useful is 1 plus omega 3 square is 0, okay? So you can go back to that picture, you got 1 here, omega 3 here, omega 3 squared here. If you add these three vectors, this omega 3 and omega 3 squared, you will get minus 1, right? So minus half, plus root 3 by 2 minus root 3 by 2 will cancel, it will go to minus 1 and then it will go to 0. Okay, so this 1 plus omega 3 squared going to 0 is very important. Go back to that picture and convince yourself that happens. So once you have that, you can quickly construct an inverse for S. S inverse ends up looking very similar to S, right? It's almost similar except for this 1, 1, 1, 1, 1, 1 is the same. And you can see what has happened here. Omega 3 squared shows up in the diagonal. Here you got omega 3 on the diagonal. Okay. And then omega 3 squared is on the off diagonal here, this side. Here you've got omega 3 on that side. Okay, so that's all. So that's the only little shift here. But other than that, it is exactly looking very similar to S. And you can convince yourself by multiplying. This is an assignment for you. Check it. Do S times S inverse is I. You can show that by using this property. Okay, and then you will also have to use omega 3 power 4 and all. 1 omega 3 cubed is 1. All of that you have to use here to show this. So once you do this, the power is very easy. I'm not going to show you here. It's just S inverse and can be done very easily. Okay. So there's also a column view you can take. Okay, so I keep saying row. It turns out for the same circulant matrix, the columns also have a cyclic property. If you see the first column and the second column is a cyclic downshift of the first column. Third column is a cyclic downshift of the second column, right? So there's also a column view here. So if you take a column view instead of a row view, you get a very similar looking thing. So it's the same matrix, right? So the same sort of theory goes through, the eigenvalues, eigenvectors, all of them are the same. But what is the column view? Instead of ABC, I want to think in terms of ACB. If you do that, you just have to write it like this, okay? So the crucial idea here is that this omega 3 inverse is the same as omega 3 squared. So B beta plus C beta squared, I'm going to write it as C times beta inverse plus B times beta power minus 2. Remember, beta power 3 is 1, right? So let's think about this. So beta power 3 is 1. Okay, so beta power 3 is 1 for any cube root of unity. So beta will become beta power minus 2 and then beta squared will become beta power minus 1. Okay, so this is an important little observation. There's nothing much going on here. So instead of writing C beta square, I'll write C beta inverse. Instead of writing B beta, I'll write B beta minus 2. So this is the way in which sometimes this is described, the same property. Instead of row wise, you'll describe it on the column. So but then you'll have to do a beta inverse here. Okay. So the same thing here. So instead of B omega 3, C omega 3 squared, the same beta, you just do it at C and bring it this side, you'll get the answer. Okay. So this is the column view. Sometimes the column view is taken, in which case you will get this inverse showing up in the calculation of the eigenvalue. Okay. Okay. So now we saw cube root, and I also mentioned that later on we'll see how this extends to the complex nth root. So let's quickly see what this complex nth root of unity. We're going to call this Wn. Wn is e power I 2 pi by n. This is cos 2 pi by n plus I sin 2 pi by n. For some particular n, you may get Wn to be this. Okay, this is a complex number on the unit circle. Angle is 2 pi by n, magnitude is 1. Right, so that's Wn. What will be Wn squared? We just move by the same 2 pi by n counterclockwise, right? So Wn squared will be here, angle will be 4 pi by n, 2 pi by n plus 2 pi by n, and it will be on the unit circle. So likewise, you may keep on doing. You will get Wn power k, which is cos 2 pi k by n plus I sin 2 pi k by n, e power I 2 pi k by n, and angle is like 2 pi k by n here. Okay, so this is Wn power k. Okay, so this is all just notation. Sometimes it's useful. And if you keep repeating it, Wn power n goes to 1. Okay, so that's why all these guys are called nth roots of unity. So if beta is an nth root of unity, beta will belong to this set. 1 Wn squared till Wn power n minus 1. So these are all the nth roots of unity. After this, it will repeat, right? You multiply by 2 pi by n again, you will come here. I mean, rotate by 2 pi by n again. It will go on the same circle over and over again. So these are the cube roots of unity, nth roots of unity, and the solutions of x power n minus 1. You can see why this, you see this will be connected to the transform of length n vectors. If you cyclically shift them, the same transform will work, the same sort of theory will work without any difference whatsoever. Okay, so some of the properties are useful. Beta per n is 1, absolute value of beta is 1, beta inverse is beta bar, right? So all of these things you can see, right? When absolute value of beta is 1, so you see beta times beta bar is actually 1, so beta bar is beta inverse. You can also see that beta inverse is beta power n minus 1. So beta bar is also beta power n minus 1. Okay, so you need not stop here, you can even use this guy and go to the next equality. And here is very non-trivial property. So this is the extension of that 1 plus omega 3 plus omega 3 square equals 0, no? The extension is this guy. If you take any nth root of unity, it can be any of these things, and if you do 1 plus beta square all the way till beta per n minus 1, there are only two possibilities. It's either n if beta is 1, okay, that's easy to see, or it will be 0. Any other non-zero nth root of unity, if you add them all together, you will get 0. This is not very difficult to show. You can show it very easily. Okay, so this is useful. This nth root of unity and all the associated ideas are useful when you deal with eigenvalues and eigenvectors of n by n circulant matrices. Okay, so with this, I'll conclude this lecture. Thank you very much.